In this video, we're going to continue with studying quantum mechanics and the 4 identifying factors of each electron within an atom. Last time we talked about those 4 identifying factors as being first the principal quantum number, giving us an idea of the distance of the electrons from the nucleus. The second identifying factor, the subshell, and before moving from the principal quantum number or the shell, we have 7 different options, and that comes from the row on the periodic table, the 7 rows. And then we have the subshell, S, P, D, or F, and that is found by the area of space in which the element is located on the periodic table. We previously took our periodic table and turned it into how it actually should be listed, and we can see those 4 areas of space, the S, the P, the D, and the F. And that gives us information about the shape the electron creates as it moves around the nucleus. Then, the third identifying factor is the orbital that it is in. It's found by the position of the element within the specific subshell. There's only 1 orbital for S, 3 for P, 5 for D, and 7 for F. Those specific orbitals look like this. The S orbital is a spherical shape in which 2 electrons can fit into that S orbital. After the 1s, it goes to the 2s. And then the p's actually have 3 orbitals. The px, the py, and the pz. 2 electrons can fit into this orbital, 2 into this, and 2 into this. As a reminder, why is it that the s only has 1 orbital? Well, the rule is that only 2 electrons are allowed per orbital, so this S only allows 2 electrons. But when you look at the periodic table, every time you go across the periodic table, there are only 2 elements in the S subshell. But when we move across the P subshell, you will count 1, 2, 3, 4, 5, 6. So with 6 electrons going across the P, and each orbital only allowed to hold 2, we have 3 different orbitals, 3 different areas of space in which electrons can be located. Then we also spoke about the electron spin, and each electron will have a specific spin. We said it's similar to the Earth, where the Earth is rotating around the sun, but it's also spinning along its axis. Well, as the electrons are flying around, they also have a spin to them. If you have 2 electrons in the same orbital, they must have opposite spins. It has to do with their magnetic interference. As the electron spins, it creates a magnetic field, and those magnetic fields will interfere with each other, so they must have opposite spins. What we're going to do in this video is we're going to walk through the periodic table, looking at each one of the elements and the electrons within the element, and identifying a couple of factors about them. For the quantum mechanical description, we're first going to write down what is called the electron configuration notation. Then we're going to write down what is called the orbital notation. And then we're going to write down what is called the description of the last or final electron. So we're going to look at 3 different areas, 3 different ways that we identify the electrons on the periodic table, or within an atom on the periodic table. So first off, we're going to start with hydrogen. And we're going to look at hydrogen, and we're going to identify these pieces of information about hydrogen. So when we look at hydrogen on the periodic table, Hydrogen on the periodic table is in row number. Now, remember, I often refer to this as energy level, but technically, if we look back at our notes, this is the principal quantum number, or shell. So the principal quantum number, or shell, for hydrogen is 1. How do we know that? Because hydrogen's in row number 1. This periodic table has it printed here on the outside, row number 1. Then, what is its sublevel? Well, the sublevel is identified by S, P, D, or F. Well, it's clear that it's in the S subshell. So 1s. How many electrons are we putting in to that 1s subshell? Since hydrogen's the very first one, we're putting 1 electron in. So the way we identify it is 1s, and then we put a superscript of a 1. The S subshell contains only 1 orbital. It contains only 1 orbital. If we look back at our notes, there is only 1 orbital for S, and there it is, this spherical shape. So you can picture 1 electron flying around on this spherical shape. Then, its orbital notation, because it only has 1 orbital, we're going to draw it as a box. We're going to draw all orbitals as a box. Technically, we should be drawing it as a sphere. And we're going to put 1 electron in that 1s orbital. There is a spin associated with the electron, and we are identifying it as an up arrow or a down arrow. Clockwise spin or counterclockwise. The rule is we always put the clockwise spin electron, identify the first electron as a clockwise spin electron. So now, letter C, we identified all the pieces of that last electron. Now, there is only 1 electron, and it is the last one. So it's the 1s up electron. Now, at this point, we are probably confused, but I promise you, as we go through, it becomes easier and you will see the patterns. The second element we're dealing with is helium. So we find helium on the periodic table. Remember, we cut him off the right-hand side and put him right there. What principal quantum number is helium in? The principal quantum number is the first identifying factor, and clearly it's in row number 1, so we put a 1. What sublevel is it in? Well, clearly it's in the S sublevel, so we put an S. But unlike hydrogen, it's the second one over, it's number 2, so it has 2 electrons, so we write 1s2. The S orbital only contains 1 S subshell, only contains 1 orbital, so we only draw 1 box. Technically, this shouldn't be drawn as a box. It should be drawn as a sphere, but I'm not good at drawing spheres, and luckily the scientific community has decided to use boxes instead of actually drawing the orbitals as their shape. The first electron there for helium, an up spinning electron, and the rule is for electron spin, the electrons in the same orbital must have opposite spins. So if that's an up spinning or clockwise, the next electron is a down spinning or counterclockwise. So now, does this represent helium with 2 electrons total? It does. Helium is the second one over. When you look at this periodic table, you will see helium over here, but remember, for quantum mechanics, it really belongs next to here. Why do we have to have him here on the regular periodic table? Because remember, energy level number 1 can only hold 2 electrons. So helium is full with 2 electrons, just like all of these are full with 8 on the outside. Helium's full with 2 because energy level 1, or principal quantum level number 1, can only hold 2 electrons. But it's in the S subshell, so it would be over there. So its last electron, the description of the last electron would be a 1s down electron. So you can picture helium as in the 1s having 2 electrons spinning around the surface with opposite spins, and then the nucleus very, very tiny with 2 protons right in the center. We now move on, and after helium is lithium. So we write lithium, and we're going to identify where all of lithium's electrons are. So we're going to walk through the periodic table. We start with energy level 1 and we count over 2. So we write 1s2. Then we get to energy level 2. It's the first element over in the S, and so it's 1s2, principal quantum number 2 because of row 2, sublevel S, and it's the first one over. Now I want you to notice lithium is number 3 on the periodic table. Here are 2 of its electrons. Here is 1 of its electrons. The S sublevel has 1 orbital. The S sublevel has 1 orbital. Well, what's different between this 1s orbital and the 2s orbital? The 1s orbital is smaller than the 2s orbital. So we have to think of this 2s orbital being superimposed on the outside of the 1s. And lithium will have 2 electrons in the 1s flying around and 1 electron on the outside flying around in the 2s. So when we identify those electrons, you have an up and a down spinning electron, and you have an up spinning electron here. Then the last electron for lithium was the 2s down spinning electron. Now let's move on to beryllium. Beryllium, letter A. If we were walking through the periodic table, it's the second one over. So we're going to just walk through until we finally get there. We start with energy level number 1. We're in sublevel S, and we count over 2 spots. 1s, 2 spots. Then we're not there yet, so we go to 2s, and we count over 2 spots. Energy level quantum, principal quantum number 2, sublevel S, 2 spots over, 2. 1s1, 2s2. The S has 1 orbital. The S has 1 orbital. This first 1s has an up and a down spinning electron. The 2s has an up and a down spinning electron. How many electrons does beryllium have? It has 4 electrons. Here is 2 of the electrons. Here is 2 of the electrons. 2 of the electrons are in the 1s. 2 of the electrons are in the 2s, having opposite spins. What's the last electron identification? It is the 2s down. And I just found my mistake from lithium. I made a mistake. Lithium should be last electron, the 2s up. So please get that fixed if you didn't see that mistake that I made. The last electron for lithium is the 2s up. The last electron for beryllium is the 2s down. After beryllium, we go over to boron. There should be 5 electrons for boron. We need to identify where they are, how they're spinning, and all that type of thing. So, boron. Boron, we start with the same process. Principal quantum number 1, sublevel S, and then 2. So 1, S, 2. Then we go to principal quantum number 2, sublevel S, and 2 over. 1s2, 2s2. Then we go all the way over. We're in principal quantum number 2. We slide, and this is the first time that we've hit the P. So it's 2p because we're still in row number 2. There are no p's in row number 1. Row number 2, 2p, and it's the first one over, so 2p1. So the question is, does boron have 5 electrons? Yes, it does. 2 plus 2 plus 1. 2 are in the 1s orbital, 2 are in the 2s, and 1 electron is in the 2p. The s's have 1 orbital. The s's have 1 orbital, but when you look at the p's The p's have 3 orbitals. Why 3 orbitals? Because when we're putting in those 6 electrons, only 2 electrons per orbital, so there must be 3 orbitals. How do we identify these 3 orbitals? The identification for those 3 orbitals are x, y, and z. Why do they choose x, y, and z for their orbital notation? Because this orbital is along the x-axis, this orbital is along the y-axis, and this orbital is along the z-axis. This is where the electrons are going to be flying around. This is the shape the electrons make as they're flying around. So now, this is going to take a little bit of looking and processing, but we have a 1s orbital with 2 electrons. This 2s orbital is superimposed on top of this 1s with 2 electrons. Then this 2px is this axis, this point right here in the middle is pointed right there. So you've got this 2s on the outside with 2 electrons, this right here with 2 electrons flying around. Then you have this px, and because it's a 2px, it extends out this area and this area. And what did we say? How many electrons in that 2p? Just 1, and 1 electron flying around in the surface. So you have 2 electrons flying around this surface, 2 flying around the 2s surface, and then 1 flying around in this area in the 2px. So we identify the 3 orbitals as x, y, and z. We have 1s, an up and a down. We have a 2s, an up and a down, and a 2p as an up. So the electron, the orbital notation is an up and a down in the 1s, an up and a down in the 2s, and an up in the 2p. So there's 5 electrons for boron, 2 in the 1s, 2 in the 2s, and 1 in the 2p. And you can picture the atom here where you have a tiny, tiny nucleus with the 5 protons, and then the 2 electrons in the 1s, the 2 electrons flying around in the bigger sphere of the 2s, and then the 1 electron in the 2px orbital. Therefore, the last electron is the 2px up electron. Notice what happened tonight. Notice what happened with this orbital where now we have an x here, 2px up. Here, the s, we did not have a subscript because it only has 1 orbital, so there is no needed notation. But with the p, there's an x, a y, and a z. Moving to the next element, after boron, we move over to carbon. Carbon is the next element. So when we look at carbon, and we're walking through the periodic table, we start with principal quantum number 1, the row number, 1s, count over 2. So we go 1s, 2. Then we get to row number 2. We're in the s. We count over 2. 1s2, 2s2. So we've got 4 electrons. We're building the atom of carbon. Then we're still in principal quantum number 2. We get over to the second element. So it's still principal quantum 2, but we're in the p sublevel. We're in the p sublevel, and we are the second one over in the p sublevel. So carbon is number 6 on the periodic table because it has 6 protons and 6 electrons. It also has 2, 4, 6 electrons. There's the 6 electrons, 2 in the 1s, 2 in the 2s, 2 in the 2p. The s has 1, the s has 1 orbital. This p has 3 orbitals. 3 orbitals to hold electrons. Now, here's our next rule that we come across. Each orbital must be half filled before any are completely filled. So here's what that means. The S, we have an up and a down. The S, we have an up and a down. We have an up in the 2px, and we have an up in the 2py. We do not put the down in the 2px because atoms do not like to have full orbitals and half orbitals. It helps with stability to fill up these orbitals first, half full, before any of them are complete. So now when we're looking at that last electron, it's not the 2px down, it's the 2py up spinning electron. The 2py up. The next element, and I also want to point out, carbon is in column 4a. Why 4a? Because it has 4 valence electrons, 4 outer electrons, 4 bonding electrons. So let's look here. Here's principal quantum 1, here's 2. So if I put a dotted line, principal quantum number 2, the outer principal quantum number has 4 electrons because carbon is in 4a. These are the 4 bonding, 4 outer, 4 valence electrons. 2 of them in the 2s and 1 in the 2px, 1 in the 2py. 4 valence electrons. We would call these inner or core electrons. After carbon is nitrogen. Nitrogen, as we walk through the periodic table, this, remember, helium really belongs over here. We start with principal quantum number 1. We are in section S, so we go 1s. We count over 2 spots. Then we go to principal quantum number 2. We are still in the S. We count over 2 spots, 1, 2. Now we're still in principal quantum number 2, but now we're in this section, which is the P, and we count 1, 2, 3. 2p3. The S has 1 orbital, and the P's have 3 orbitals, and we label those 3 X, Y, and Z. So here we have 2 electrons, an up and a down, 2 electrons, an up and a down, and 3 electrons, but remember, each orbital must be half full before they are complete. So I don't put a down electron here, I put an up electron in the 2pz. So our last electron, our final electron, is the 2pz up spinning electron. Now, let's go back and look at carbon. So carbon here, it needed to add, so it's got 2 electrons in the 1s, 2 electrons in the bigger sphere, the 2s, 1 electron in the 2px, but now we need to add in the 2py. So now along the y-axis, 3-dimensional, there's an electron here in the 2px flying around. Now there's an electron here in the 2py. Now when we look at nitrogen, we need to add in the 2pz. And so now we're going to add in another orbital extending out to that second principal quantum number. And now we've got 1 electron flying around in the 2px, 1 in the 2py, 1 in the 2pz, 2 in the inner sphere of the 1s, and 2 in this outer sphere of the 2s, totaling a total of 2, 4, 7. 7 electrons total. Why? Because nitrogen's number 7. And when you look at the outer, there are 2 here and 3 here, which add to 5. That's why it's in column 5A, because there are 5 valence electrons on the outside of nitrogen. Now, looking forward, we're going to start looking at what these atoms do and why. Earlier, we would have written nitrogen with the nucleus and 2 energy levels, 2 electrons in the first and 5 electrons in the second. If we would have talked about what nitrogen wanted to do, we would have said, oh, it wants to gain 3 electrons. And then it would be an N with a 3 minus because it wants to get 8 electrons on the outside, so it would want to gain 3. Why does it want to gain 3? It wants to gain 3 electrons because it wants to put 1 electron here. It wants to put 1 here, and it wants to put 1 here. Then all of its orbitals would be full. But don't add those down electrons in right now because all we're doing is looking at the atom of nitrogen. I just wanted to show you what it would look like. Next, we have oxygen. Oxygen, letter A, is 1s2, 2s2, 2p4. Why is it 1s2, 2s2, 2p4? We start with principal quantum 1. We count over 1, 2 because helium's over on this side. We go to principal quantum number 2. We count over 2, so 2s. Then we get over here to principal quantum number 2, and it's 1, 2, 3, 4th. The 4th one over. The first orbital has 1 orbital for the s, 1 orbital for the s, and then 3 orbitals for the p. We have an up and a down for the s. We have an up and a down for the s. Here we have an up, up, up. Now all of them are half full. The 4th electron is the down electron here. So the final electron, we have to be very careful. For oxygen, it's the 2p. Some people will look and say, oh, it's the 2pz up. It's the furthest one out here. Remember, we went up, 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 now down. So 2px down spinning electron. My hope is that you can see that you have a down electron open here and a down electron open here, 2 open availability. So when we look at oxygen, if I were to draw oxygen like we previously did with 2 energy levels, 2 electrons, and then 2, 3, 4, 5, 6 electrons, and I asked you it's a non-metal on the right side of this stair-step line. Remember, on this side are the non-metals, and non-metals like to gain electrons. So now, oxygen, what would he want to do? Well, he'd want to gain 2 electrons because he has 6 electrons on the outside. He wants to gain 2 more to have 8, so it would become gain 2 electrons. It would become an O with a 2 minus charge because you're gaining 2 negative electrons. Well, why would it want to gain? Well, based off of quantum mechanics, it makes perfect sense. It wants 1 down electron in the 2py and 1 down electron in the 2pz. When we look at our drawing here, it's got 2 electrons in the 1s. It's got 2 electrons in the 2s. It's got 2 electrons in the 2px, but it only has 1 in the 2py and only 1 in the 2pz. It wants to put another electron in the 2py and another electron in the 2pz. Then it'll be all full. So it wants to gain 2 electrons. After oxygen is fluorine. Fluorine is 1s2, 2s2, 2p5. It's the fifth one over. 1, 2, 3, 4, 5. Fifth one over in the 2p subshell. It's got an orbital. Each s has one orbital. Each p has 3 orbitals. You have an up and a down in the s, an up and a down in the s, and then 5 electrons. Remember, it's an up, up, up. Each orbital must be half full. Each orbital must be half full before any are complete. Then we go back and we go down, down. 5 total electrons in the 2p. Then the last electron, we have to be careful. It's not the 2pz up, it's the 2pz down. So, sorry, not the 2pz down, the 2py down. So here we have 2py down spinning electron as the last electron. So now between the in principal quantum number 1 and principal quantum number 2, I'm going to put a dotted line, and we can see that in the principal quantum number 2, there are 2 electrons here, 5 electrons here, which equals 7 valence electrons. Why 7 valence electrons? Because fluorine is in column 7a. Those are the 7 valence electrons. If we were to look at what fluorine would want to do, it would want to gain 1 electron. Why would it want to gain 1 electron? To put into the 2pz orbital, and then all of its orbitals would be complete. For our last element, we're going to look at neon. Neon, we have 1s2, 2s2, 2p6. The s orbital has an up and a down. The s orbital has an up and a down. And the p orbital has an x, y, and z. It's got an up, an up, an up. And then we go back and we go down, down, down. So the very last electron we put in is the 2pz down spinning electron. Now, if I put a dotted line here between principal quantum 1 and 2 to look at the last principal quantum number is 2, I have a 2 and a 6, which gives me 8 because it's in column 8a. In column 8a. That means it is complete. It is full. It does not want to gain any electrons. It does not want to lose any electrons. That's why we call this column here the noble gases. They do not want to gain or lose any electrons. I hope this helps in understanding the 4 identifying factors of each electron. If we look at this right here, we would have 2 electrons in the 1s, 2 electrons in the 2s, the outer 2s superimposed orbital. We would have 2 in the 2px, 2 in the 2py, and 2 in the 2pz, all flying around with all the orbitals completely full. I hope this helps in understanding the 4 identifying factors for each electron within an atom.